In this video, I will be discussing about stochastic processes and probability tree. So, after discussing these finite stochastic processes, we can discuss the total probability and the Bayes theorem by Thomas Bayes. And we observe that many experiments consist of a sequence of two or many events. A probability tree provides a useful device for structurally defining the relationships within such experiments and for computing probabilities associated with possible outcomes. A finite sequence of experiments in which each experiment has a finite number of outcomes with given probabilities is a finite stochastic process. In other words, a finite stochastic process is a sequence of experiments that has finite number of outcomes. So, illustrating this one in an example, we have this example number 12 here. We are given three boxes as follows. Box 1 has 10 light bulbs of which 4 are defectives. Box 2 has 6 light bulbs of which 1 is defective. And box 3 has 8 light bulbs of which 3 are defectives. We select a box at random at first and then draw a bulb at random here. What is the probability that the bulb is defective? So here we perform a sequence of two experiments, and the first one is we need to select one of the three boxes, and the next one is selecting a bulb which is either a defective or non-defective, but the question is selecting a defective bulb. So using a probability tree, we can draw three branches here, wherein the first arrow is for choosing the first box, and the second arrow is for choosing the second box, and the third one is choosing the third box. But when you choose the first box, you can select either a defective bulb or a non-defective bulb. And so with the second box, you can still choose a defective or a non-defective bulb. Same here in the third box. But choosing a box is having a probability of 1/3 of choosing box 1. Also, having a probability of 1/3 when you choose the second box. And choosing the third box is having a probability of 1/3 because there are three boxes here. So, choosing any one of them is having a probability of 1/3. But if it happens that you have chosen box 1 and box 1 has 10 light bulbs of which 4 are defectives, wherein box 1 has 10 light bulbs of which 4 are defectives, then the probability of selecting a defective light bulbs from the first box is 4/10, while the probability of selecting a non-defective light bulb from the first box is 6/10. Also, the probability of selecting a defective light bulb from the second box is 1/6, since the second box has 6 light bulbs of which 1 is defective. So, therefore, we have a probability of 5/6 of selecting a non-defective light bulb from the second box. Also, if you have chosen box 3, there is a probability of 3/8 of selecting a defective light bulb, since the third box has 8 light bulbs of which 3 are defectives. So therefore, selecting a non-defective light bulb from the third box is 5/8 here. But in this problem, our event of interest is selecting a defective light bulb. So in the probability tree, the defective event is colored red there. And since there are three mutually exclusive paths which lead to the defective bulb, the sum of the probabilities of these paths is the required probability. So tracing the path for defective light bulbs, we have probability of selecting a defective one can happen in three possible cases. And the first case is when you choose the first box. And after choosing the first box, choosing a defective light bulb given that you have selected the first box. And the second case is choosing the second box and then selecting a defective light bulb from this second box given that you have chosen the second box. And the third case happens when you have chosen the third box here times the probability of selecting a defective light bulb from this third box given that you have chosen the third box. So solving for the probability of selecting a defective light bulb is equal to the probability of drawing the first box here and then selecting a defective light bulb from this first box. So this is 1/3 times 4/10. And then the second case is choosing the second box, which has a probability of 1/3, and then selecting a defective light bulb from this second box, which is 1/6. So we have 1/3 times 1/6. And the third case happens when you have chosen the third box, which has a probability of 1/3, and then selecting a defective light bulb from this third box, which is 3/8. So therefore, we have 1/3 times 3/8. So multiplying these fractions, we have 2/15 as the product of 1/3 and 4/10 plus 1/18 as the product of 1/3 and 1/6 plus 1/8 as the product of 1/3 and 3/8. Hence, adding these three fractions, we have 113/360, which means that there is a probability of 113/360 of selecting a box at random, then draw a defective light bulb from this box that you have chosen. Now, let's proceed to our next example here. A coin weighted so that the probability of obtaining a head is 2/3 and the probability of obtaining a tail is 1/3. Now, if a head appears in a single toss, then a number is selected at random from the numbers 1 through 9. But if a tail appears, then a number is selected from the numbers 1 through 5. What is the probability that an even number is selected? So, solving this problem is to aid our solution by a probability tree. And the first branch is a head, because when you toss a coin, one of the possibility is obtaining a head and the other possibility is obtaining a tail. But if you have the outcome of a head, when you toss the coin, you can choose a number from numbers 1 through 9. So it could be an odd number or an even number there. And also when you have the tail result, when you toss the coin, you can choose a number from 1 through 5. So it could be an odd or an even number. But obtaining a head when you toss a coin is having a probability of 2/3 because the coin is weighted to have a head of 2 out of 3 chances. And of course, the probability of obtaining a tail is 1/3. But when you have a head as a result of tossing the coin, there is a probability of 5/9 of choosing an odd number, since there are 5 odd numbers from the numbers 1 through 9, namely 1, 3, 5, 7, and 9. But there are only 4 even numbers from the numbers 1 through 9, which are 2, 4, 6, 8. So therefore, the probability is 4/9. But if you have a tail result when you toss a coin, you can have only a probability of 3/5 of choosing an odd number, since there are 3 odd numbers from the numbers 1 through 5. And these are 1, 3, and 5. But we have only a probability of 2/5 of choosing an even number, since there are 2 even numbers from 1 through 5. And these are 2 and 4. And you notice that in my probability tree, I have the events of even numbers colored red. So obtaining the probability of selecting an even number can happen in 2 cases. And the first case, when you have obtained a head during the tossing of a coin. And then This will be multiplied by the probability of obtaining an even number given that you have a head as a result of tossing the coin. And the second case is the probability of having a tail as a result of tossing the coin times the probability of selecting an even number given that you have a tail as a result of the tossing of the coin. So, tracing our probability tree, we have the probability of having a head, which is 2/3, and then the probability of selecting an even number when given a head as a result of tossing the coin is 4/9. So we have 2/3 times 4/9 plus the probability of having a tail when you toss the coin, and that is 1/3, times the probability of selecting an even number given a tail as a result when you toss the coin, and that is 2/5 there. So multiplying these fractions, we have 8/27 as the product of 2/3 and 4/9 plus 2/15 as the product of 1/3 and 2/5. So adding these two fractions, we have 58/135. So therefore, we say that there is a probability of 58 out of 135 chances of selecting an even number after tossing the coin. And this happens in two possibilities, wherein the first case is having a head during the tossing of a coin, and the second case, which is having a tail when you toss the coin. Now, let's proceed to our next example here. From a box containing 4 white balls, 3 yellow balls, and 1 green ball. 2 balls are drawn one at a time without replacing the first before the second ball is drawn. What is the probability that 1 white and 1 yellow are drawn here? So, here, let us represent the events. So the event W is the representation of drawing a white ball, and the event Y is the representation of drawing a yellow ball. And take note that in this problem, drawing 1 white and 1 yellow does not specify that white is the first ball and yellow is the second ball. So there are two possibilities here. The possibility is having a white in the first draw and yellow in the second draw, or having a yellow in the first draw and white in the second draw. As long as you have 1 white and 1 yellow obtained from these two draws. So obtaining 1 white and 1 yellow is the probability of drawing a white during the first draw and drawing a yellow during the second draw, given that you have drawn a white ball from the first draw. And the second case happens when you draw a yellow one during the first draw and then multiplying it by the probability of drawing a white ball given that you have drawn a yellow ball during the first draw. So drawing the white ball from this box is 4/8, since we have 4 white balls out of 8 balls from this box. And then drawing a yellow ball from the same box without replacing the first ball to the box is 3/7, since there are 3 yellow balls there out of 7 remaining balls from the box, because you have drawn already the first ball. Or it can happen when you draw first the yellow ball and there are 3 yellow balls from the box, so 3 out of 8 balls from the box, times the probability of obtaining a white ball from a box of 7 remaining balls, and there are 4 white balls there, so 4 out of 7 balls is the probability of drawing a white ball given that you have drawn a yellow ball during the first draw. So multiplying these fractions, we have 12/56 as the product of 4/8 and 3/7 here, and then added to 12/56 as the product of 3/8 and 4/7 here. So we have 24/56, and when you reduce this one by dividing the numerator and the denominator by its common factor, which is 8, then we have 3/7. Then therefore we say that there is a probability of 3/7 when you draw 1 white and 1 yellow from the box containing 4 white balls, 3 yellow balls, and 1 green ball without replacing the ball after the first draw, and also without specifying whether the first one is white or the first one is yellow. As long as you have 1 white and 1 yellow, when you draw the 2 balls in succession from this box of 8 balls. Now, illustrating this one using a probability tree, we have 3 arrows here, since we can draw a white or a yellow or a green ball from this box. And drawing a white ball from this box is having a probability of 4/8, since we have 4 white balls out of the 8 balls in this box. And we have a probability of 3/8 of drawing a yellow ball from this box, since there are 3 yellow balls from this box of 8 balls. And also a probability of 1/8, since we have only 1 green ball from this box of 8 balls. And after drawing the first ball, we can draw our second ball without replacing the ball after the first draw. So you can draw a white or a yellow or a green here. And drawing a white ball from this box is 3 out of 7, since we have a remaining of 3 white balls from this box out of the 7 balls here. And the probability of drawing a yellow ball from this box after you have drawn a white ball is 3/7, since we have 3 yellow balls from this box of the remaining 7 balls. Also, we have a probability of 1/7 of drawing a green ball after you have drawn a white ball in the first draw. But if you have drawn a yellow ball during the first draw, you can choose a white ball or a yellow ball or a green ball from this box. And the probability of drawing a white ball is 4/7, because we still have 4 white balls from this box, since it was yellow that you have selected during the first draw. But drawing a yellow ball from this box after the first draw is having a probability of 2/7, because you have drawn one of them during the first draw. And a probability of 1/7 of drawing a green ball from this box, since we still have 1 green ball from this box after you have drawn a yellow ball during the first draw. But the last case, if you have chosen a green ball during the first draw, and choosing a ball in the second draw can be in 2 cases only. You can draw a white ball in the second draw, or you can choose a yellow ball in the second draw. But we cannot choose a green ball during the second draw, because there is only 1 green ball in this box, and that green ball was chosen already during the first draw. So we have a probability of 4/7 in selecting a white ball in this box of 7 balls, because 1 ball is chosen already during the first draw. And the probability of 3/7 of selecting a yellow ball in the second draw, since you have drawn a green ball during the first draw. So tracing the path that has a red color at the end, we have choosing a white ball during the first draw, which is 4/8, times the probability of choosing a yellow ball during the second draw, which is 3/7. Or you can choose a yellow ball during the first draw, which has a probability of 3/8, times the probability of 4/7 of drawing a white ball during the second draw. So adding these 2 paths, we have a probability of 3/7. 3 out of 7 chances of drawing 1 white and 1 yellow in succession from this box of 4 white balls, 3 yellow balls, and 1 green ball in succession from this box, without replacing the first ball after the first draw. Now let us present to you the Theorem of Total Probability. In this section, we consider experiments with sample spaces that can be divided or partitioned into 2 or more mutually exclusive events. And this study involves a further application of conditional probabilities. So the theorem states that if the events B sub 1, B sub 2, up to B sub n constitute the partition of the sample space S such that the probability of each of these partition is not equal to 0 for each of them, then for any event A of the sample space S, the probability of obtaining the event A is equal to the probability of B1 times the probability of A given that B1 has occurred plus the probability of B2 times the probability of A given that B sub 2 has occurred plus and so on and so forth to the last product, which is the probability of B sub n times the probability of A given B sub n has occurred. So giving a proof of this theorem, we have suppose the events B sub 1, B sub 2, B sub n form the partition of the sample space S, that is, the events B sub I are mutually exclusive events and their union is the sample space S. Now, let A be any other event of the sample space S, and this can be represented by the green portion inside the rectangular box here. And you can see that in this drawing, the whole rectangle is being partitioned by B sub 1, B sub 2, B sub 3, B sub 4, up to B sub n. So the whole rectangle is the disjoint union of these partitions, B sub 1, B sub 2, up to B sub n. And let this green portion as another event of the sample space S. Thus, event A is the intersection of the sample space and the event A, which is colored green in the drawing. But the sample space S can be represented by the disjoint union of all these partitions, B sub 1, B sub 2, B sub 3, up to B sub n. And this will be intersected with the event A. So applying the distributive property for these sets, we have B sub 1 intersected to A, union, B sub 2 intersected to A, union, and so on and so forth to the last intersection, which is B sub n intersected to event A. And we know that B sub I intersection with A are also mutually exclusive events. And you can see that in the drawing, that event A is the disjoint unions of B sub i's intersected to A. So, taking the probability of these sets, we have probability of A is equal to the probability of B sub 1 intersection A plus the probability of B sub 2 intersection A plus and so on and so forth plus the probability of B sub n intersection A. And since B sub I and A are not independent events, we can write the probability of B sub 1 intersection A as the probability of B sub 1 times the probability of A given B sub 1 has occurred. And this probability of B sub 2 intersection A can be represented by the probability of B sub 2 times the probability of A given that B sub 2 has occurred, plus and so on and so forth to the last probability, which is the probability of B sub n intersection A. And this can be written as the probability of B sub n times the probability of A given that B sub n has occurred. So, illustrating this one in an example, we have three machines, machine A, machine B, machine C, produce respectively 50%, 30%, and 20% of the total number of items in the factory. And the percentages of defective outputs of these machines are 3% from machine A, 4% from machine B, and 5% of the machine C. If an item is selected at random, what is the probability that the item is defective? So, representing our events, we have event D as the event that an item selected is a defective one. So, the probability of selecting a defective item from this factory can happen in three possible cases. And the first case, where we can choose a defective item given that this defective item is produced from machine A. Or you can choose a defective item given that it was manufactured by machine B. Or selecting a defective item given that it was produced by machine C. So we have three possibilities here. Now solving for their probabilities, we have a probability of 50% since the probability of the production of machine A is 50% for the factory production times the probability of the defective items produced by this machine A, which is 3%, and the probability of the production of B for the factory, which is 30% times the probability of the defective outputs from this machine, which is 4%, plus the probability of the production of machine C for the factory, which is 20%, times the probability of the defective outputs from this machine, which is 5% of the time. So multiplying this 50% and 3%, we have 1.5% plus the product of 30% and 4%, which is 1.2%, and the product of 20% and 5%, which is 1%. So adding these three probabilities, we have 0.037 or 3.7%. Therefore, we say that the probability of selecting a defective item can be obtained using the Theorem of Total Probability, that you account all the possibilities here. Defective items produced by machine A, defective items produced by machine B, defective items produced by machine C. So obtaining their probabilities of producing defective items for each machine, we can compute for the probability of selecting a defective item in this factory, which is 3.7%. Now, observe that we can also consider this problem as a stochastic process, as illustrated in the tree diagram below, that the production of the factory is produced by the three machines, machine A, machine B, and machine C. Now, the contribution for the factory from machine A is 50% and only 30% contribution from machine B and 20% contribution of the production from machine C. But machine A can produce defective items or non-defective items. But this machine A can produce on the average of 3% defective items. So therefore, the production of non-defective items is 97%. But machine B can produce also defective and non-defective items. But it's given in the problem that machine B can produce at the average of 4% defective items. So therefore, we have a production of 96% non-defective items from machine B. Also, machine C can produce defective and non-defective items. And it's given in the problem that on average, this machine C can produce 5% defective items. So therefore, we say that we have a probability of 95% of producing non-defective items from this machine C. So tracing the paths which has an n of a defective one, we just multiply their probabilities in each path. So selecting a defective item from machine A is having a probability of 50% times 3%. But selecting a defective item from machine B is having a probability of 30% times 4%. As well as selecting a defective item from machine C, which is having a probability of 20% times 5%. That is why we have a total probability of 3.7%, which means that the probability of selecting a defective item from this factory is 3.7%. Now, let us proceed to our next example here. 3 members of a faculty association have been nominated for the office of the president. The probability that Mr. Ipple will be elected is 30%. and the probability that Mr. Misa will be elected is 50%, and the probability that Mr. Pelayo will be elected is 20%. Should Mr. Ipil be elected, the probability for an increase in membership fees is 80%. Should Mr. Misa or Mr. Pelayo be elected, the corresponding probabilities for an increase in membership fees are 10% and 40% respectively. What is the probability that there will be an increase in membership fees? So to solve this problem, we need to represent our events here. Let I be the event of the increase in membership fee, and Y be the event of Mr. Ipil's presidency, and then M is the event of Mr. Misa's presidency, and P is the event of Mr. Pelayo's presidency. So we can solve for the total probability of the increase in membership fee. And to solve for this total probability that there will be an increase in the membership fee will be computed as the sum of the three cases. The first case is when Mr. Ipil won the election. The second case is when Mr. Misa won the election. And the third case is when Mr. Pelayo won the election. And we know that Mr. Ipil's winning probability is 30%. And it is also given in the problem that he will impose an increase of the membership fee by 80%, added to the probability of Mr. Misa of winning the election, which is equal to 50%. And the probability of Mr. Misa of increasing the membership fee is 10%, plus the probability of Mr. Pelayo's winning the election by 20% multiplied to the probability that he will increase the membership fee of 40%. So multiplying these probabilities, 30% times 80%, that's 24%, added to the product of 50% and 10%, which is 5%. Also added to the product of 20% and 40%, which is 8%. So the total probability that there will be an increase in membership fee is 37%. Or in other words, there is a probability of 37% in increasing the membership fees of this faculty association. Now observe that we can also consider this problem as a stochastic process as illustrated in the tree diagram below. So at the beginning, during the election, three candidates are vying for presidency. Those were Mr. Ipil, Mr. Misa, and Mr. Pelayo. The probability of winning for Mr. Ipil is 30% and Mr. Misa is 50%, as well as the probability for winning the presidency for Mr. Pelayo is 20%. But if Mr. Ipil will win the election, there will be a probability of 80% in increasing the membership fee. So for sure, a 20% probability that there will be no increase in the membership fee. But if it was Mr. Misa who won the election, there will be a probability of 10% in increasing the membership fee. So therefore, 90% probability that there will be no increase in the membership fee. But if it was Mr. Pelayo who won the election, there will be a probability of 40% in increasing the membership fee. So therefore, a 60% probability that there will be no increase in the membership fee. So solving for the total probability that there will be an increase in the membership fee is to trace the path for the increase in membership fee. So tracing the first path for the increase in the probability, which is colored red at the end, is the product of 30% and 80%. And this will be added to 50% times 10%. And the last path, which is the product of 20% and 40%. So adding these three products from the 3 paths, we have a total of 37%. In other words, there is a probability of 37% that there will be an increase in the membership fee for this faculty association. Now, at this point, it's time to present to you the Bayes rule. So in this section, we will study a very famous formula of Thomas Bayes. Thomas Bayes was born in London and was the son of a Presbyterian minister. Bayes, who was also ordained and began his ministry by assisting his father, was elected as a Fellow of the Royal Society of London in 1742. He published several theological papers, but he was very famous for his paper on probability, which was published after his death by a friend who found it among his effects. And this work is very noteworthy because it was the first discussion of inductive inference in precise quantitative form. So what is this Bayes theorem? The Bayes theorem states that if the events B1, B2 up to Bn constitute a partition of the sample space S, where the probability of this B sub I is not 0 for all the i's from 1 to n, then for any event A in S such that the probability of this A is not 0 is given by this formula. The probability of B sub I given A is equal to the probability of B sub I times the probability of A given B sub I divided by the total probability of A, which is given in the whole denominator of the probability of B sub 1 times the probability of A given B sub 1 plus the probability of B sub 2 times the probability of A given B sub 2 plus and so on and so forth until to the last product, which is the probability of B sub n times the probability of A given B sub n for all I from 1 to n. And because this is a theorem, we need a proof for this theorem. And the proof starts by the definition of the conditional probability. And we know that the conditional probability states that the probability of B sub I given A is equal to the probability of B sub I intersection to A divided by the probability of A. But the numerator can be written as the product of the probability of B sub I times the probability of A given B sub I by applying the probability of an intersection, because the two events are not independent here. They are dependent to each other. So therefore, the probability of this intersection is equal to the product of the probabilities of dependent events. But the denominator is a total probability of A. So therefore, substituting the total probability of A in the denominator, the probability of B sub I given A is equal to the probability of B sub I times the probability of A given B sub I divided by the total probability, which is expressed in the Theorem of Total Probability for A, which is the probability of B sub 1 times the probability of A given B sub 1 plus the probability of B sub 2 times the probability of A given B sub 2 plus and so on and so forth until the last product, which is the probability of B sub n times the probability of A given B sub n. And the resulting equation forms the Bayes theorem. Now, let us illustrate this Bayes theorem in an example here. Now, we will use our previous example from our example 15. 3 machines, machine A, machine B, machine C, produce respectively 50%, 30%, 20% of the total production of the factory. And the percentages of the defective output of these machines, machine A, machine B, machine C, are 3%, 4%, and 5% respectively. Suppose an item is selected at random and is found to be defective, then what is the probability that the item was produced by machine A? So this is a problem that needs the application of the Bayes rule, the Bayes theorem. So first, let us represent our events. Let A be the event of the machine A production, and let D be the event for the production of a defective item. So solving for the probability that the item was produced by machine A, given that it was a defective item, can be solved by this Bayes rule formula. So the probability that the item selected at random was produced by machine A, given that it was defective, is given by the probability of the production of machine A times the probability that it was defective, given that it was produced by machine A, all over the total probability of the defective items for the whole factory. So solving for the numerator, we know that the probability of the production of machine A is 50%, and the probability that it is a defective item, given that it was produced by machine A, is 3%, all over the total probability, which we have solved it already from example 15 in the previous slides. We have the numerator of 0.015 and the denominator is the sum of these three products here, which is 0.015 plus 0.012 plus 0.01. So adding the denominator, we have the sum of 0.037. So simplifying this fraction, this is equal to 15 over 37. So therefore we say that there is a probability of 15 over 37 that the item selected at random was produced by machine A, given that it was found to be defective. So this is now the application of the Bayes theorem, the Thomas-Bayes rule. Now here, let's apply again the Bayes rule to our previous example, which is example 16 in the previous slide. 3 members of a faculty association have been nominated for the office of the president. The probability that Mr. Ipel will be elected is 30%. The probability that Mr. Misa will be elected is 50%. And the probability that Mr. Pelayo will be elected is 20%. Should Mr. Ipel be elected, the probability for an increase in membership fees is 80%. Should Mr. Misa or Mr. Pelayo be elected, the corresponding probabilities for an increase in membership fees are 10% and 40% respectively. If someone is considering joining the association after the election but delays his decision for several weeks only to find out that the fees have been increased, what is the probability that it was Mr. Pelayo who won the election as the president of the association? So first, let us represent our events here. Let event P as Mr. Pelayo's presidency. In other words, it was Mr. Pelayo who won the election. And event I as the increase in the membership fee. So solving for the probability that it was Mr. Pelayo who won the election, given that we know already that there was an increase in the membership fee, this is equal to the probability of Mr. Pelayo winning the election times the probability that there is an increase if he won the election, divided by for the total probability that there will be an increase in membership fees. And we solved this denominator already in example 16 in the previous slide. So solving our numerator, we have the probability of Mr. Pelayo winning the election, which is 20%, multiplied by the probability that there will be an increase if he will win the election, which is 40%, divided by the total probability, which is represented by the sum of these 3 products here. So adding the 3 products in the denominator, we have the denominator of 0.37. So simplifying this fraction, we have 8 over 37. Hence, there is a probability of 8 over 37 that it was Mr. Pelayo who won the election, given that we know already that there is an increase in the membership fee in the faculty association. So, in this problem, we have illustrated again the application of the Bayes rule, the Thomas-Bayes theorem. Now, let us solve this last problem here. A truth serum given to a suspect is known to be 90% reliable when the person is guilty and 99% reliable when the person is innocent. If a suspect was selected from a group of suspects of which only 5% have ever committed a crime, what is the probability that a person selected to be judged from a group of suspects will be judged guilty? Letter B. What is the probability that the person selected to be judged from a group of suspects will be judged innocent? Letter C. What is the probability that he is guilty when the suspect selected was already judged innocent? Letter D. What is the probability that he is innocent given that the serum indicates that he is guilty here? Now, to solve this problem is to illustrate the given things in the problem using the Venn diagram here. And the whole sample space, we know it's represented by a rectangle using the diagram proposed by John Venn. And the whole sample space is being divided into two. One is the event of the guilty suspects, and the other one is the event for innocent suspects. So there in the drawing, the guilty event is represented by the blue color, and the event for the innocent is in white color there. So it is given in the problem that the probability that the suspect is guilty is 5%, and the probability that the suspect is innocent is 95%. But let us draw also the event of judging the suspect as innocent by representing this one in the Venn diagram as an oval colored red. So this event is the event of judging as innocent for the suspect. And we know that it is given in the problem that the probability of judging it guilty given that the suspect is guilty is 90%. So in the diagram above, it is represented by the blue color minus the red oval there. And the probability of judging the suspect as innocent given that he is guilty is 10%. And in the drawing, it is represented by the part of the oval that is common to the blue part. And also the probability of judging the suspect as innocent given that he is innocent, and it is represented by the part of the oval that is common to the white part, which is 99%, and the probability of judging the suspect as guilty given that he is innocent is the white part minus the red oval there, and it is 1%. So, for the first question, what is the probability that the person selected to be judged from the group of suspects will be judged guilty? Can be solved by solving for the total probability of judging the suspect as guilty. And this can be done in two cases here. The first case is judging the suspect as guilty given that he is innocent, and also judging the suspect as guilty given that he is really guilty of the crime. So the probability that the suspect is innocent is 95% times the probability of judging him guilty given that he is innocent, which is 1%. And this will be added to the second case of the probability that the suspect is guilty, which is 5%. And the probability of judging him guilty given that he is really guilty of the crime, which is 90%. So the first product is equal to 0.0095 and the second product is equal to 0.0450 here. So adding these two decimals, we have 0.0545, or in percentage, that is 5.45%. In other words, there is a probability of 5.45% that the suspect will be judged guilty here. So moving to the second question, what is the probability that the person selected to be judged from the group of suspects will be judged innocent? And this can be solved by solving for the total probability of judging the suspect as innocent. So solving for this total probability is to add the two cases here, wherein the first case is judging the suspect as innocent given that he is really innocent of the crime. And this will be added to the second case of judging the suspect as innocent given that he is really guilty of the crime. But we know that the probability that the suspect is innocent is 95%, and this will be multiplied of judging him innocent given that he is really innocent of the crime, which is 99%. Added to the second case, which is the probability of the suspect to be guilty, is 5% here, multiplied to the probability of judging him innocent even if he is really guilty of the crime, which is 10%. So multiplying 0.95 by 0.99, the product is 0.9405. And this will be added to the product of 0.05 and 0.10, which is 0.0050. So adding these two decimals, we have 0.9455, or in percentage, this is 94.55%. So we say that there is a probability of 94.55% of judging the suspect as innocent. And this is represented in the red oval in the Venn diagram. Now let's proceed to the third question here. What is the probability that he is guilty when the suspect selected was already judged innocent? So solving this question is to apply the Bayes rule here, which is the probability that the suspect is guilty given that he is already judged as innocent. And this is equal to the probability that he is guilty times the probability that he was judged as innocent given that he is really guilty of the crime, divided by the total probability for judging the suspect as innocent, which we solved already in the second question. So the numerator, which is equal to 0.05 times 0.10, divided by the total probability for judging the suspect as innocent, which is represented by the sum of the two products here. We have the numerator of 0.005 and the denominator as the sum of 0.005 plus 0.9405. So adding the denominator, we have the sum of 0.9455. So simplifying this fraction, we have 50 over 9,455. So in simplest form, this is equal to 10 over 1,891. Or in decimal, this is 0.005288. Or in percentage, this is less than 1%. In other words, we have a probability of 0.5288% that the suspect is guilty given that he was already judged as innocent. Now, let us proceed to the last question here. What is the probability that he is innocent given that the serum indicates that he is guilty here? So solving this problem is to apply the Bayes rule here, which is the probability that the suspect is innocent given that he is really judged as guilty. and the numerator is the probability that he is innocent times the probability that he is judged as guilty given that he is innocent of the crime, divided by the total probability of judging the suspect as guilty. And we have solved this denominator already in our first question there. So our numerator, which is the product of 0.95 and 0.01, divided by the sum of these two products here, which we have solved it already in the first question up above. So our denominator is equal to 0.0545. So simplifying this fraction, we have 95 over 545. And in simplest form, this is equal to 19 over 109. Or in decimal, this is 0.1743. Or in percentage, this is 17.43%. In other words, there is a probability of 17.43% that the suspect is innocent given that he was already judged as guilty. And that's it. If you learned something today, please check out my channel for more videos like this and click subscribe. Click the notification bell below so you'll get notified whenever I'll be posting a new video. Don't forget to like this video to show your support. And always remember to math your way up. Thank you.